So, so let me start. So, good morning and good afternoon, everyone. It is a great pleasure to welcome you all to the 2025 APCTP Colloquium. And I would also like to extend a special welcome to all of our colleagues and friends joining us from all around the world online. Before we begin today's special lecture, it is my great honor to introduce two distinguished individuals who has joined us today. First, I'd like to welcome the director of the Asia Pacific Center for Theoretical Physics, Professor Misao Sasaki.
Thank you.
Professor Sasaki
Yeah, sorry. Yeah, go ahead.
is the 10th director of our center and globally renowned scholar in the field of general relativity and cosmology. As a former professor at the Yukawa Institute for Theoretical Physics at Kyoto University, he has received numerous honors for his groundbreaking work. Most recently, he has elected as ISGRG Fellow 2025 by International Society on General Relativity and Gravitation. It is a great distinguished honor reserved for the selected member for the top researcher worldwide. Furthermore, he is the recipient of the 2024 Benjamin Lee Professorship Award, which is presented by our center to honor exceptional achievement in the theoretical physics and his profound impact on the cosmology. And please join me in giving a warm welcome to Professor Sasaki.
Thank you. Thank you, Jungi. Good morning and good afternoon for some people. So I'm Misao Sasaki, as Jungi introduced me, the current president of the APCTP. I'm very happy to announce this opening of this 2025 Colloquium series, which will consist of 8 talks by the world experts in various fields of physics. I'm sure that everybody will enjoy it and get inspiration from all these talks. Before I just handing this to Jungi, to the lecture, Chair Jungi, let me just briefly introduce this APCTP. As I have shown in this slides, this was established in 1996. The first founding president was Xian Yan, and next year is the 30th anniversary. And up to now, we have so far right now the 19 member countries and regions from the Asia Pacific regions. And we are trying to expand this to more countries and regions, as well as to expand the activity to worldwide, not just limited to Asia Pacific regions. So I hope you will have a chance to visit us and also support us for future activities. Thank you. All right, I hand it to Jungi.
Thank you, Misao. Now it is my honor to introduce our speaker for today. Please join me in giving a warm welcome to Professor Igor Klebanov from the Princeton University. Professor Klebanov holds a prestigious title of Eugene Higgins Professor of Physics at Princeton University, where he has directed the Princeton Center for Theoretical Science. After he earned his PhD in theoretical physics from the Princeton in 1986, he conducted his postdoc work at the Stanford Linear Accelerator Center, so-called SLAC, before returning to the Princeton as a faculty member in 1989, where he has remained ever since. His primary research focused on the quantum field theories, and it's a dual description by the gravity, and or so-called ADS-Shefty correspondence. His expertise in the physics of strong interaction is demonstrated by his leadership role as a director of Simon collaboration on confinement and the QCD strings. Professor Klebanov's exceptional contribution has been recognized with numerous awards, including 2022 Oscar Klein Memorial Lectures and medals from the Stockholm University, and the 2023 Dirac Medal from the International Center for Theoretical Physics, or ICTP, which is considered one of the highest honor in the theoretical physics. He has also been elected to both the United States National Academy of Science and the American Academy of Arts and Sciences. Today, Professor Klebanov will deliver a lecture on the non-perturbative formulation of quantum chromodynamics as it relates to the strong interaction and confinement. With that, let us officially begin the 2025 APCTP Colloquium with a lecture by Professor Igor Klebanov. Please.
Okay, thank you very much, Jungi, and thank you for the invitation. It's a real honor to be the first speaker of this year's Colloquium series. So let me try to share the screen. Okay. Yeah, you can see it, right?
Yes, we can see.
Okay, so so the title of the colloquium is Strong Interactions, Confinement, and Strings. And I think Jungi already described basically what it is about. I will give a kind of, as requested, an overview of QCD and the beginnings of series of strong interactions. But then I will I will talk about the more recent work over the past 3 years on Hamiltonian lattice gauge theory for Schwinger model and for other two-dimensional gauge theories, and then end with the most recent paper I wrote about supersymmetry in a joint QCD2, which is a model which is a kind of toy model for QCD. Okay, so let me start with a bit of philosophical introduction about string theory. You often hear about it as the leading hope for unifying all known interactions, including strong or nuclear force, electromagnetic, weak force, and the gravitational force into a consistent quantum theory. It's definitely a candidate for consistent quantization of gravity. And some have even dubbed it the theory of everything, right? Which is a bit of a tongue-in-cheek term. But I will talk about mainly a different aspect of string theory, not as a unification of all forces, but as a dual description of the strong force or of quantum chromodynamics. And actually, string theory began even before quantum chromodynamics. It started as basically people noticed some features of excited states of hadrons which were string-like. As you know, there are two types of hadrons, which are mesons and baryons, right? Mesons are like pion, kaon, rho, j psi, and so on. And baryons are what nuclei are made of, proton, neutron, and also strange baryons, and so on. And the characteristic scale of the strong force is about GeV, or giga electron volt. And it's also a correspondingly a very short range force with about 10 to the minus 15 meters range. So it's not long range like electromagnetism. And that's actually related to confinement. It's related to the fact that gluons don't really propagate as massless particles, but it is 100 times stronger than the electromagnetic force. It's responsible for holding atomic nuclei together. So without the strong force, there would be certainly no world as we know it. Okay, so a very important juncture was the conjecture of substructure of hadrons in terms of quarks by Gell-Mann and Zweig. Zweig called them aces, actually. And they realized that the hadrons observed to date, I mean, this was around early 60s. By then, strange hadrons were known, and they combined them into certain multiplets of SU3 group, which is an approximate symmetry because according to the conjecture back then, it rotates as 3 light quarks, up, down, and strange. Up and down are really light, but strange is quite a bit heavier, but it's still light enough for some purposes. At that time, what we now call heavy quarks, which is charm bottom and top, were not known yet. So here are the multiplets of baryons. So these are the pseudoscalar mesons, pions, kaons, and the eta. And this is the baryon octet, the SU3 multiplet. Okay, so that still doesn't look like string theory. But then a very big breakthrough was right around 53 years ago. Basically, quantum chromodynamics was invented, really gelled during the 1972-73 academic year. And there was a very important conference, ICHEP at Formulab, exactly 53 years ago. It was September 6 to 13 at Fermilab. And there you can actually find this contribution by Fritsch and Gell-Mann. They were talking about the advantages of having an octet of colored gluons. Before then, the mediator of the force between quarks was just assumed to be one particle, not an octet. There were such models, but they basically conjectured an octet and a joint representation of the color group. The color group acts on the 3 color states. And then within months, the SU3 Young-Mills theory for strong interactions was formulated, especially through the work of Gross and Wilczek and Politzer, who noted that it's asymptotically free, which I will discuss in a second. It looks like a non-abelian version of electromagnetism. There is a kinetic term for gluons, which is F mu squared. Then the quark fields psi, the fermionic fields, and the gauge coupling between quarks and gluons. And the important thing is that the field strength is, unlike in QED, also involves a quadratic term in gluons. So even if you throw out the quarks, there will be self-interactions of gluons. Okay, so basically, that was an incredible breakthrough. The observation of asymptotic freedom, namely that the force, the theoretical observation of asymptotic freedom, namely that at high momentum transfer, alpha strong, which is the equivalent of the fine structure constant, actually weakens as 1 over the logarithm. It's sort of the opposite of what happens in QED. There, the force gets stronger at high energies, but here it weakens. And that makes it a kind of perfect quantum field theory, because at very short distances, it regulates itself. It becomes free. So there should not be any pathologies associated with the short distance. It does not need to be embedded in a bigger theory, unlike say QED needed to be embedded in electroweak unification. But opposite side of this asymptotic freedom is that in the regime where bound states, hadronic bound states form, the theory is extremely hard to solve. It becomes strongly interacting, and this is evidenced by this growth of alpha strong at low momenta, below 10 GeV. So this is a problem that people are still trying to solve, but a lot of progress was achieved over the past 50 years due to lattice calculations, because thanks to the work of Wilson, Kreutz, and others, this theory has a beautiful lattice regularization, which is amenable to numerical calculations. So as I mentioned, the gluons, while they're present as massless fields in the Lagrangian, you basically don't see any mass terms for gluons. They're forbidden by gauge invariance, just like the photon mass term. But unlike photons, they're not really propagating degrees of freedom at the speed of light. In fact, they kind of get confined into, so each gluon comes in 8 color states, but they form colorless hadrons. If there are only gluons, then they will form so-called glue ball states. But quarks also get confined into mesons and baryons. And precisely how this happens, we still don't understand. I mean, in experiments, one can see for a very short time a quark propagating, but then it forms a jet. It basically gets dressed up by other quarks and forms an energetic bunch of particles. So you never observe free quarks or gluons as asymptotic states. You only observe colorless bound states. They're the only ones that are recorded in the detectors. By the way, if you want to ask a question, feel free to interrupt. I don't know how it works, or maybe questions are at the end. I don't know, but if you have a pressing question, you can probably interrupt. Okay, so this confinement problem, it's for years it was kind of regarded as #1 problem in theoretical physics, precisely how QCD works. And around 25 years ago, there were these so-called Clay Millennium problems. Each one was originally, for solution, one would get 1 million. Maybe it's been upgraded a bit since then due to inflation. But basically, the precise statement of the problem doesn't even involve quarks. It just involves a mass gap in a pure quantum Yang-Mills theory, namely that massless gluons really bind into massive bound states and nothing propagates to the speed of light. This is called the appearance of a mass gap, just the fact that the lightest bound state weighs something. In reality, it weighs something on the order of a couple hundred MeV, mega electron volts. And so back 25 years ago, it said, but no proof of this property is known. And there's still, it's not known. And in fact, over the past 20 years, there hasn't been that much work on it because people have been mainly working on other things. So the status of the problem is unsolved. But then a few years ago, several of us had the idea to apply for a collaboration to revisit confinement, maybe not to prove it, but at least to understand it better. I mean, most of the classic results on confinement are many years old. And that's what we're working on now. We're into the 4th year of the collaboration. This beautiful image that one of the PIs, Grigory Tarnopolsky, has created symbolizes a proton, essentially. You see that there are 3 quarks of different colors inside this crystal ball. So that's our mission. So let me just review a little bit about what it would take to prove confinement in pure Yang-Mills theory. So that theory has Wilson formulation in terms of sum over plaquettes. Basically, on each link, say you can have a hypercubic lattice, and on each link of the lattice, there is a unitary matrix. For SUN gauge theory, it's an SUN matrix. And you have a sum of plaquette terms where you multiply these matrices around each face of the lattice and then trace them and then add the Hermitian conjugate. And then you do it with faces in all directions. So then Wilson's criterion for confinement is the area law of the Wilson loop, namely of a large Wilson loop. Namely, if you take a large Wilson loop, which involves this, say, large rectangle, if you do strong coupling expansion where you take this G, the lattice coupling G, to be very large, then this action term is small, so you can expand in it. And then you find that the leading contribution to the expectation value of a large Wilson loop is when you kind of fill it in by these elementary squares. So the leading contribution as a result then is of order e to the minus the area, because you have to fill in the area. And that's exactly the area action. As we'll see, it corresponds to the large tension of the string that you form, because you can think about it as a kind of creating a probe quark-antiquark pair, then separating them to this distance, propagating them in time, and then rejoining. So, and then if these quarks here have a linear potential, you get e to the minus the product of the distance here times time. So that's the sought area action. And you can prove it in the strong coupling expansion. That was clear already in the 70s. But the problem is that this is sort of on the opposite side of where we want to be. We really want to be in the weak coupling limit, namely the lattice coupling G0 has to be sent to 0 rather than to infinity. And this is due to the asymptotic freedom, really. This is the scale dependence of the coupling constant. So this is, there is a famous phenomenon called dimensional transmutation. I think it's a terminology invented by Sidney Coleman. And it basically goes as follows. The question is, how does a dimensionless parameter G transmute into QCD scale, which is the scale of the lightest bound states, which is of order a couple hundred MeV. So the way it happens is that you solve this this surrounding RG equation, which was derived indeed in 1973 by Gross and Wilczek and by Politzer. The crucial thing is this minus sign here. So that means that the coupling strength decreases at short distances. Then if you look at what happens with how this scale transmutes, you see that what should happen is that in strong coupling limit, the scale of everything is just 1 over lattice spacing, which is a very large scale. But then it's actually by finding out where this coupling blows up in the infrared and calling it lambda QCD, you find that it's actually not 1 over A0, but it's multiplied by this exponentially small factor, e to the minus a constant over G0 squared. So these two factors, one diverging and the other one going to 0, balance out to create this QCD scale. So basically out of the UV logarithms, you get the scale, which is like the argument of the logarithm. And to prove confinement in the right limit would mean that you have to prove, this is just an estimate kind of, but you have to prove that the bound state masses and the square root of the string tension should be pure numbers times this quantity. And the problem of numerical simulations is basically to compute these pure numbers. They're indeed finding that everything is determined by this one scale, and just the ratios are the question mark. So the fact that it works was already suggested in the mid-70s by the work of Wilson and Kreutz, and now it's understood much better. You can basically, you know that the size, say, of a hadron is around a femtometer, and you can go to lattice spacing, which is about 1/10 that much. So you can resolve hadrons pretty well. And this is the spectrum calculated exactly 20 years ago in a paper by Chen, Morningstar, and others for pure gauge SU3 theory. You see that there is indeed a mass gap. There is no massless gluon. There is 0++ glue ball, 2++, and so on. And the problem is how to compute the ratios. So numerically, I think now people can achieve even better precision because working on a 4-dimensional torus with, I think, 1,000 lattice sites per side is already feasible, and people kind of moved on to theories with fermions. So numerically, it's quite clear that this mass gap is generated, but what the theorists are after is a kind of either a proof that this happens or a pretty good argument for what the mechanism of confinement is. And I think there is no broad agreement. I mean, it's kind of model dependent because there are theories in 3 dimensions where one mechanism applies, in 4D it's another mechanism, in 2D it's yet another. So it seems like a good time to revisit a lot of the ideas from the 70s and 80s.
So I have a question in the previous slide. So that is a 4D numerical simulation, 4D case.
Yeah, this is 4D. Yeah.
Right. Okay, thank you.
Yeah, yeah. In 3D, the precision is even higher. Yeah, these are, yeah, I think these are spins. These are actual spins. Yeah, it's quite a well-known paper. Yeah, you can find it in various reviews. Yeah, I didn't put in the HepTH number, but it's exactly 20 years ago.
Okay.
Okay, so one thing everyone agrees on is that what happens with non-abelian gauge fields is that unlike in QED, where if you pull an electron and positron apart, you get a dipolar pattern, here the field strength gets collimated into a kind of flux tube or QCD string whose thickness is of order a femtometer also. And this is from a lattice simulation. So what you're supposed to find is that the force between quark and antiquark, while coulombic at distances smaller than femtometer, becomes linear at distances bigger. And I'll show a plot from also an old simulation where it's very evident. Another feature is the spectrum of excited higher spin meson. It's called the Regge trajectory, where as you increase the spin, you see that the mass squared grows linearly with spin. This is called the Chu-Frautschi plot or Regge behavior. And this is still perhaps like one of the best evidences for string theory relevance to real world, because string theory explains this linearity of the trajectory. It's basically a relativistic string spinning around its center and elongating as the spin increases. Okay, so that's QCD. It's obviously hard because confinement or mass gap has not been proven in over 50 years. So now I will talk about various toy models where theories try to simplify the problem or make it add extra symmetry or go to lower dimensions, and that's what in practice people are mostly doing. So these toy models, yeah, these are the spherical cows. I'm sure you've heard about the spherical cow joke. Basically, it's like replacing, thinking about the spherical cow as a kind of highly symmetric distortion of the real cow. So let me talk about several toy models. And they're of quite different nature, actually, these toy models. So one toy model which John Gee mentioned is the ADS-CFT correspondence. This is replacing basically, say, SUN, Young-Mills theory, which is confining, we believe is confining, by the maximally supersymmetric theory. So it's then SUN coupled to some scalar and fermion fields in the joint representation. It's called N=4 super Young-Mills theory. And about like almost 30 years ago, there was great excitement that this theory also in the large N limit appears to be described by string theory on a particular 10-dimensional space. It's called ADS5 x S5. So S5 is just a sphere in 6 dimensions, or a sphere with 5 internal dimensions. But ADS5 is a kind of hyperboloid. So this is a kind of funny picture of a hyperboloid, which is styled by cows to remind us that this is a toy model for real world. So this theory actually is not confining. It's basically whatever gauge coupling you set, it does not run. And a miracle happens when the theory becomes strongly coupled, because then the corresponding geometry becomes weakly coupled. So this is not the main point of my talk, so I will not explain it in detail, but this duality originated right around 30 years ago from studying wonderful objects in string theory called Dirichlet brains, or D-brains, whose relevance was realized by the late physicist Joe Polchinski. And they're basically particular defects where open strings and they serve as endpoints for open strings. So what happens is that there are particular 3-dimensional D-branes, and when you stack n of them on top of each other, you get SUN super Young-Mills theory. So this duality has been studied in, by now, tens of thousands of papers, and while it's not proven, it's been tested in great detail. But unfortunately, this in itself does not teach us about confinement, because this theory is just not confining. Here, the gluons really are staying massless, and there is no dimensional transmutation here. Beta function is exactly 0. But then there was a trick that came about for, very soon after the original ADS-CFT papers, was to put these D-branes at the tip of a cone, the tip of a 6-dimensional cone. This was, for example, done in my paper with Witten in 1998. And then the ADS-CFT duality, basically, instead of the sphere, S5, you get the base of the cone. But very importantly, you can break supersymmetry down to N=1, for example, rather easily. And for N=1 supersymmetry, there are actually confining Young-Mills theories. For example, the pure N=1 supersymmetric Young-Mills theory is believed to be confining. And proving confinement in that theory is in itself a very worthy goal. So then one particularly nice space is something called the conifold. It's a very popular space to study in string theory, because when you take a Calabi-Yau 3-fold cone, This one is described by a constraint on 4 complex variables that sum of their squares is equal to 0. You can actually derive the metric on the base of this cone, and it looks like a circle bundle over a product of two spheres. So you have here 2 usual 2-dimensional spheres, and the psi is a circle angle bundled over them. The interesting thing is that this no longer has the topology of a 5-sphere. It has a topology of a product of 2-sphere times a 3-sphere, which will be very important actually for deforming this model to obtain a confining theory. Okay, then, so with Witten, we did a bunch of work to determine what gauge theory this is. It turns out to be SUN cross SUN with some bifundamental chiral superfields. And this theory is just an n-equal minimally supersymmetric conformal field theory, which in itself has been studied in detail. And it's dual to ADS 5 cross T11. T11 is the name for the base of the cone. So then after a series of papers, actually it was figured out how to obtain dimensional transmutation in this gauge gravity duality. Basically, what one needed to do is to, instead of only 3 branes, we add MD5 branes and wrap them over the 2-sphere near the tip of the cone. That gives a non-conformal theory, SUN plus M cross SUN, which exhibits some complicated pattern of running. But then with Strassler, we found a very explicit metric, which is simple enough. It's a 10-dimensional metric, which turns out to be dual to a confining gauge theory. We called it the warp deformed conifold because H is the warp factor. This DS6 squared is the metric on the deformed conifold. And the deformation is the fact that you generate this epsilon squared on the right side. It turns out that without this deformation, the metric sort of is not nice. It has a naked singularity. Okay, so this is basically what happens. Like the pure ADS metric as a function of R is just L to the 4 over R to the 4, and it blows up at small r. The metric that we earlier, with a naked singularity that ignores the deformation, has it sort of behaves nicely for a while. So here the warp factor has this extra log, and it behaves nicely for a while, but then it turns over and hits 0. And when H is 0, it means that this whole transverse space shrinks to 0, and there is a big trouble. But then, thanks to the appearance of this epsilon, which is a blown up 3-cycle, you actually get a perfectly nice monotonic warp factor. And the string that sits at this minimal radial coordinate at the bottom of this warp throat is the confining flux tube. It has a finite tension, which is set by epsilon. So this is a kind of physicist proof of confinement in this model, because unless you put in this epsilon deformation, the space is singular, but to make it non-singular and smooth, we needed to put in confinement, basically. So this model has also been studied a lot. I mean, nowhere near as much as ADS 5 cross something, but it does describe confinement. For example, you can use it to compute quark-antiquark potential. It's a rather simple exercise. It's a semi-classical calculation. And you see that it starts out as approximately coulombic and then becomes linear. Qualitatively, it's very similar to the QQ bar potential obtained from lattice gauge theory. This is the lattice gauge theory result. You see the interpolation between coulombic part and linear part. So at least we get something qualitatively similar out of the space. but this theory, although it runs logarithmically, it's not really asymptotically free. So we would like to do better, but it's proven to be very hard. So a dream which I think still lives on is to do something similar for real large NQCD, not this somewhat contrived theory with two gauge groups. Okay, so that's sort of one toy model which I've spent a lot of time on, but it's already about 25 years old, and I think we're ready for more models like this, and it would be great to come up with one. So now let me switch to something even older and seemingly simpler, but also quite subtle, which is actually one of the earliest toy models of confinement. This model is, you need to know quite a lot. You need to know about 10-dimensional supergravity, curved spaces, algebraic geometry to construct this model. But here comes like a much older model called the Schwinger model, which was used to describe sort of binding of charges. This model is about as old as I am. It was born in 1962. And is basically, Schwinger originally studied quantum electrodynamics in 1+1 dimension with a massless charged fermion. And he obtained actually that this theory is just a theory of a free bound state of fermion antifermion called the Schwinger boson of mass E over square root of pi. So for massless fermion, which is the strong coupling limit, it becomes an exactly solvable model. Basically, this is it's a very tightly, essentially point-like bound state of electron and positron in the linear potential. In 1+1 dimensions, electrostatic potential is mathematically linear, which is sort of gives the confining force. And another interesting thing is that one can also add a topological parameter called theta angle, analogous to the theta angle in 4-dimensional QCD. So here is a pretty striking plot. It's more sociology than physics, but it's a plot of the number of citations to Schwinger's original paper per year. So you see it started pretty low, then it jumped a lot during the time of QCD because people said, oh, it's a kind of simple model of confinement. And also it was solved by Coleman using bosonization. So it was a playground for studying bosonization. So it became quite appreciated and popular, but then it started becoming sort of old news and had a relatively low point, like around 2005. But then if you look at the last decade, it keeps going up and up. And actually in the highest number of citations per year was 2024. And who knows, maybe this year we'll even surpass it further. So why is that? I mean, it's everyone dreams of writing a paper like this, right? That 60 years after it's written suddenly becomes very popular again. And I think the reason is actually the quantum revolution. Basically, there is a lattice gauge theory approach, which can be studied both using usual computers and also quantum simulators. And there is a very simple model called the Kogut-Susskind Hamiltonian model for Schwinger model. It was actually, the basic idea was by Kogut and Susskind, but then Banks, Susskind, and Kogut wrote this paper, which I will review, which is a very, very simple model. It reduces to kind of fermions hopping on the lattice with long-range interactions. And people have actually built in the lab quantum simulators for this model. I think so far they cannot. So this is a slide with such a simulator from already quite long ago. I will not explain it because it's a bit far afield from me, but there are such simulators, and what my collaborators and I have been doing is just simulating it on the usual computer. And the Hamiltonian approach makes it just like a quantum problem. It's not like Wilson's Euclidean problem where you Monte Carlo. Here you just can diagonalize the large matrices. You basically on each site you have, so in 1 + 1 dimensions, a Dirac fermion is 2-component. And the idea of staggered fermion is that you put upper component on even sites and lower component on odd sites. So you have a fermionic degree of freedom on each site. And this is the Hamiltonian. And these are the discrete electric fluxes, Ln, which are these operators. And this is the hopping term with the gauge field in between. So this model has been studied using strong coupling expansion and numerically already for 50 years. That's when the paper was written. In this Hamiltonian formalism, it's important to put in Gauss law constraints, namely that the difference between fluxes is just the charge. But there are some funny subtleties. For example, the definition of charge on even and odd sites is really different. For even sites, you have to put C dagger C, but for odd sites, it's really C dagger C -1. And this was, it's really, yeah, I can't explain it in this short time, but basically because of this, you, in a compact space, you have fermions that have filling, which is very important. So this Gauss law is not fully translationally invariant. And this is, but it can be solved in terms of the charges. So you can, on an open line, you can completely eliminate the Ln's in favor of the fermions, or the fermionic charges. So what people, this has been studied in numerically in hundreds of papers. You have this fermionic formulation, but then you can go to Jordan-Wigner transformation and replace these CNs by Q bits. Like here, X means Pauli sigma X, Y means Pauli sigma Y, and Z means Pauli sigma Z. And you can express everything in terms of these qubit variables. You see that the Hamiltonian has 3 terms. One is the hopping term, this is the mass term, and then this is the Coulomb energy term coming from Ln squared. So this is the form in which people were simulating it already in the 70s. So you can say, okay, this is a very simple model. What more can you learn about it? And we thought we would just learn it as a warm-up. But then we actually noticed something new that was overlooked 50 years ago, which is what is the right definition of massless theory on the lattice. Basically, this M-lat, usually people were taking it to be 0 for massless theory. But it turns out that that's not the optimal choice. And in fact, what the right choice is to take M-lat to be minus E squared A over 8. So the right relation between the lattice and continuum mass is related by this mass shift. So what's the advantage of that is because at M = 0, there will be some discrete anomalous chiral symmetry on the lattice. Basically, people understood that that the translation by one site is like chiral symmetry because it flips even on odd sites. And even on odd sites are upper and lower component of the fermion. But there are these subtleties due to the staggered definition of charge. So it's not, the Gauss law itself is not symmetric. And it turns out it can be essentially made up by this, this shift. And then you see that the shift by one lattice unit accompanied by a shift of theta, which is really due to the chiral anomaly, exactly preserves the Hamiltonian. So these two, then the symmetry emerges for m equals 0 or m lat being equal to this number. Okay, so this means that one can realize at least discrete anomalous chiral symmetry in this model. And it turns out that this mass shift in practical terms improves things quite dramatically. For example, Kruse, Tarnopolsky, and Shin found that the easing phase transition that happens at theta equal pi, it's a kind of quantum phase transition at a special mass. Before, people were always finding it to be tantalizingly close to 1/3. They were finding 0.333. But through this, because of this improved precision, you can tell it's not exactly 1/3. And also the strong coupling expansions, which go back to 50 years ago, turn out to improve rather dramatically because they were doing them for this mu equals 0, but we're claiming that one should instead set mu equal to -1/4. And then a very simple Padé extrapolation for the mass gap in this theory gives this number, which is extremely close to 1/square root of pi. It's basically less than 0.1% away from the exact results. Well, before it was maybe at best 10% or something like this. So somehow this proper implementation of chiral symmetry on the lattice seems quite crucial for understanding these simple models of confinement. So this is one thing that we did a couple years ago, and I think it is being used by groups that specialize in putting this model on a quantum computer or on a simulator. But then there is a more complicated model, which is a two-flavor Schwinger model. And this model, as I'll show, has a lot of similarities with two-flavor QCD in 4 dimensions. This model for massless fields actually is not gapped. It's really a conformal field theory, and it has SU2 cross SU2 symmetry. It's described by a massless compact boson. But then, so that's very clear, but what happens when you turn on a very small mass? And actually, people sort of understood it, but there is one very mysterious point, which is theta equal to pi, where actually the charge conjugation symmetry is spontaneously broken, and there are 2 degenerate vacua. This is also believed to be the case for 4-dimensional QCD. But this is a simpler theory, so one can quite explicitly see this double degeneracy. So this is our phase diagram at theta equal pi as a function of the 2 fermion masses. You see that there is a region where charge conjugation symmetry is broken, and it's bounded by 2 of these easing phase transition critical curves. And this is the theory of a massless scalar field, which is when both fields are massless. But then there is a very miraculous thing that happens when both masses are equal and much smaller than the gauge coupling, the sort of strongly coupled regime. This theory actually exhibits dimensional transmutation that was overlooked for all these years. And this can be seen, so first of all, this is actually from a paper by Kreutz. The phase diagram in QCD looks rather similar qualitatively. I mean, this rotation by 90 degrees is just a different convention for theta. But you see that this is just a rotated version of this figure. So there is let me advertise a paper which is 49 years old, but it's really an amazing paper by Sidney Coleman called More About the Massive Schwinger Model. I think it's one of the most nicely written papers I've ever read, and there is a lot of beautiful stuff in it. And actually it posed some puzzles that people are still trying to solve. But in particular, it posed a puzzle about the state equal pi behavior. But what Coleman did is he applied bosonization to the two flavors and derived the effective Lagrangian, and everything worked very nicely. Essentially, one of the plus field becomes massive, the minus field stays light, and you get an effective sine-Gordon model. And then from this model, one can see that how the mass gap turns on for theta equal to 0 or any theta not equal to pi, it turns on as m to the 2/3. So it's just power law gap. But then this expression altogether vanishes when theta is pi. So what happens then? And it wasn't clear, I think, at least, for example, Howard Georgi wrote a paper 3 years ago saying that maybe there is really a line of fixed points stretching to non-zero m. But we looked at the effective field theory analysis and concluded that there is an energy gap, but it's exponentially small compared to the UV scale, much like in QCD. And the analysis actually, what happens is that while this leading operator cancels, there is a next operator with a dimensionless coefficient. So it's a sine-Gordon with a marginal operator. And this sine-Gordon model, so this was derived by Coleman, but he didn't fully analyze it. But in fact, this is a Brzezinski-Kosterlitz-Thouless flow diagram for this model. And so there is a well-known phase diagram, which in fact basically won a Nobel Prize back in 2016. And we're interested in the SU2 symmetric flow, which is just along this trajectory. And so this is the compact boson CFT. As you turn on a small mass, the theory flows away to a gapped phase. And one can solve the RG equations, and you see that they're asymptotically free. So as the theory flows to the infrared, you develop the mass gap, but it turns out to be exponentially small in this parameter g²/m². So when m is much smaller than g, you get truly tiny energy gap. And this is the prediction of our analysis. And then we tried to test it numerically using this lattice theory with the mass gap. And this theory is in some ways even nicer than, it's even nicer than the one flavor model. After the mass shift, it truly has a discrete chiral symmetry, which is not anomalous. So it's extremely crucial for this model. And using numerical methods, we determined this phase diagram, which is, so these are the easing transition lines. And here it's very hard to resolve the width of this. This is really exponentially small width. As you can guess, it's hard to see numerically the exponentially small quantities, but we see all indications for it. So this is still like requires further numerical work to fully test this idea, but I think the theory appears really QCD-like in a somewhat unexpected way at the special theta equal to pi value. Now, where people are doing active numerical work is at theta equal to 0. So here there are 4 light particles with masses of order m to the 2/3. And the lightest one is SU2 triplet of pions, and then followed by the singlet sigma meson. A lot like in QCD, but here the sigma meson is not a resonance, but it's a bound state. And Coleman predicted that it's heavier than the pion by a factor of √3. And for example, a recent Hamiltonian calculation by Atsuko Ito and collaborators basically is getting the √3 to very good accuracy. It's a kind of new improved result based on this Hamiltonian with a shifted mass. So the mass shift is extremely important precisely in the region of strong coupling, where the mass is much smaller than G. Okay, so this is another example of QCD-like toy model, which it's actually a completely UV theory, and embedded in it there is this very interesting infrared dynamics, which I think should be studied further. Okay, and then this is the last topic of my talk, which is...
sorry, can I ask something about?
Yes, yes.
So this model, there's no actual string theory calculation. Is there a string theory calculation in this model?
No, no. Well,
Right.
no, here we're just studying this model as a gauge theory.
Right. But there is a sign Gordon, so maybe is there a Pohlmeier reduction kind of relation, and can you do some string?
Yeah, it hasn't been done.
Okay.
Yeah, it's certainly just this effective sign Gordon model with beta equal to square root of 8 pi, which is the kind of borderline value, right? That's why it was not fully analyzed by Coleman. I think it was not fully clear then, or maybe the information did not percolate.
Right, and then there's this O of M4 terms, right? And then probably, yeah.
Mm-hmm.
Okay, thank you.
yeah, this model is related to SU2 tiering model, actually, which is also asymptotically free. I mean, this is sort of classic stuff from the 70s, which we are rediscovering. But I think the fact that at theta equal pi, there is this, basically, usually we say the BKT flow is when you flow here in this region and you flow to the fixed line. But we're looking at the other quadrant where you flow away from the CFT. So it's, there is asymptotic freedom here, and then you flow away to the infrared and generate this tiny energy gap. Yeah, and we're sort of trying to test this prediction of effective theory numerically some more now.
Also, the sign Gordon is supposed to be integrable for some values of the coupling.
Right. Yeah,
I don't know if you kind of, yeah.
Yeah, no, we're aware of some of this, but yeah, certainly Coleman's result about the square root of 3, that's very much based on integrability. That's
Okay, thank you so much.
yeah, thank you. Yeah, so now I just want to talk about, so far I talked in this 1 + 1 dimensions about U1 gauge theory, but there are, of course, non-abelian theories, which are also models of confinement. For example, the 't Hooft model, right, the SUN gauge theory. And that is, it's a model which is solved in the large n limit, but we've been looking at another version of this model, which is sort of more stringy in a way, which is where you replace the quark by a gluino. So you have an adjoint Majorana fermion coupled to a SUN gauge field. And this looks like a non-abelian version of Schwinger model, which has a lot of very interesting features and many topological sectors and things like that. So let me tell you a little bit what we've been doing with that. So first, those of you who know about the 't Hooft model, that's another model which is 51 years old or something like that. It was solved using light cone gauge, and he obtained the bound state integral equation where phi of y is just a distribution. This x is the momentum fraction, which goes from 0 to 1, the momentum fraction of quark in the quark-antiquark bound state. And he derived this beautiful equation and solved it numerically, obtaining masses of mesons. Each one has a kind of 1 or 2 Regge trajectories. And you see this linear behavior with the excitation number of mass squared grows linearly. So since 't Hooft's paper, there were thousands of papers citing it with various numerical solutions. In the last few years, there are actually analytical results. Fatih, Lukyanov, Zamolodchikov invented a beautiful method to at least approximate meson masses to high accuracy for one value of quark mass, and recently Litvinov and Shirokov generalized it to all equal quark masses. So there is actual activity even on this model. But this model is maybe not the best model of QCD because there are no adjoint degrees of freedom, right? In 1+1 dimensions, the gluon field is not propagating. So what I started doing back in the early 90s was couple an adjoint fermion to this model, like a gluino, and try to study whether we can solve this model using light cone quantization similar to 't Hooft. And turns out that this model is not solvable because you get an infinite system of coupled equations, but still, like, you have enough power. There is something called discretized light cone quantization to determine a few low-lying states with good accuracy. And an interesting thing is then when you take this, first of all, this is also a finite model. There are no divergences at all in this model. When you take the strong coupling limit, namely m equals 0, you find that there is a gap. So it's a gapped model. It has a mass gap. And the lightest state is a fermion, not a boson, like a 3-body state rather than a 2-body state. So we played with this model over 30 years ago, but we returned to it in the last few years, partly because of this collaboration, because it has some pretty amazing features that are only now coming to light. So one feature is that this model has a kind of discrete analog of the theta angle, which was noted by Witten in '79, where you basically put an antiquark on one end of space and quark on the other end, or 2 antiquarks, 2 quarks, and so on, up to n-1. So there are basically n separate sectors determined by the number of probed quarks at spatial infinity. And these different sectors are hard to access in light cone gauge. You really want to be in usual equal time quantization. Another exact result about this model is that one can prove that it has a mass gap, because you can reduce this model at m equals 0 to a coset model, which turns out to have vanishing central charge. It's a gauge WZW model. Basically, the adjoint currents are SUN level n. And this coset, it's easy to calculate central charge, and it's 0. So this proves that there are no gapless excitations, so there are only massive bound states, as we saw numerically. But then it has the following remarkable feature, that while it's gapped, it actually has no confinement. There is no area law of Wilson loop. One can argue heuristically that in this topological infrared model, there is no notion of area. Therefore, a large Wilson loop cannot have an area law. And this was conjectured 30 years ago in my paper with David Gross, Matitson, and Smilga. And it included various arguments, including finding a perimeter law solution of the loop equation, but it still had the status of conjecture rather than proof, I would say. But then a few years ago, there were some concerns raised in this nice paper by Charman, Jacobson, Tanizaki, and Unsal. They pointed out that there is a 4-fermion operator which preserves all the regular symmetries, which is of Gross-Neveu type. And they argue that this operator can actually get induced and destroy the conclusion that, that the Wilson loop has perimeter law. So this launched a lot of activity, and I've written several. I returned to this model and learned a lot more stuff than I knew 30 years ago. So one thing that we pretty quickly realized is that in the continuum limit, one can argue that this term cannot be induced because it violates the UV finiteness of the theory. So, and indeed, another argument is that it breaks the non-invertible symmetries of the model, which was in this nice paper. So it's usually trumpeted as a result due to non-invertible symmetries, but one can also have more pedestrian arguments for why this happens. But still, people were concerned that if you do a lattice regularization of this model, this operator can still creep in, because on a lattice, it's very hard to realize these non-invertible symmetries. So this made us sort of try to write down a lattice Hamiltonian similar to the one I showed you for Schwinger model. And at first, it wasn't clear how it would work because there are fermion doubling issues. A single Majorana fermion is a problem, seems like. But it turns out that the Hamiltonian approach solves these problems very nicely, and one can really write the lattice Hamiltonian for this model. It was in this work with my colleague Silvio Pufo and two graduate students at Princeton, Ross Dempsey and Benjamin Shogart. Ross just moved to MIT to be a Pappalardo Fellow. So they actually did a lot of computer simulations, computer diagonalizations of this Hamiltonian, and obtained the results that we had no idea about before. Basically, we could compute, for example, the bilinear condensate of trace psi bar psi to pretty good accuracy, and compute some bound state spectra, look at different topological sectors using this model and the circle. So it's a very useful model. And very recently, in a paper that just came out a couple of weeks ago, Silvio Pufo with students Dempsey, Gluck, and Shogart implemented a new numerical method for infinite lattice for SU2 and SU3 gauge theory, and plotted the string tension as a function of mass. And this very clearly vanishes at m equals 0, just like, so the vanishing of string tension means that there is a perimeter law and not area law, but as soon as you turn on the mass, you have, as soon as you turn on the mass, you have confinement and have area law. Okay, so this is just the numerical stuff. And then let me end with an analytic surprise about this model, that this model actually becomes supersymmetric for a specific mass of the gluino, not when it's massless, but when its mass is this. And this was initially argued also like 30 years ago using light cone gauge, but it was always very mysterious how this happens. And just 2 months ago, we wrote a paper with Edward Witten and Pufo and Shogart, where we established this supersymmetry, and it actually is very subtle. It relies on a kind of subtle anomaly mechanism, which I don't think people have seen before. So one can actually write the covariant expression for the supercurrent, and it includes two terms, the term cubic in the fermions and the term linear in the fermions. And one has to use the anomaly equation for the fermion bilinear, which includes this. This is essentially Schwinger anomaly. And without this term, there would be no supersymmetry. But so when we wrote the supercurrent and components, we get these 4 components of the supercurrent, and using this anomaly equation, we see the conservation And it kind of follows from a cancellation between classical and quantum terms within just classical equations and the quantum anomaly. So this solves a problem of many years. I'm quite happy that it worked out. And we also found some additional models with additional massless fermions, and we're sort of thinking about them too. And this model in the string sector also exhibits spontaneous breaking of supersymmetry. One can see numerically the Galstino mode on the confining string. Basically, there is a confining string, and on the string, there is really a Galstino, which is a Majorana fermion. You can see this exactly at supersymmetric value of the joint mass. You see this gapless mode. So that's another application of the lattice theory. Okay, so yeah, I've went through quite a few topics. So let me just summarize. So what have I done? Well, one thing I have not done is prove confinement in asymptotically free 4D gauge theory. That remains a very difficult open problem. And I think there are some new ideas about fractional instantons. I'm not qualified to talk about them, but there is pretty vigorous activity both within, you know, we've had a number of collaboration workshops where people spoke about this. So there is a lot to learn about dynamics of these confining flux tubes and how they form and so on. But what I mainly told you about are these toy models in 1+1 dimensions, which are surprisingly QCD-like. For example, this two-flavor Schwinger model at theta equal pi, where effective field theory suggests dimensional transmutation. And we see some numerical support for this, but would be here, I wouldn't be surprised if it can be proven rigorously. Because this model is very simple relatively. It's actually UV finite for the full model. Then we also studied the kind of soup-topped Hooft model where you replace quark by a gluino, which is similar in some ways to the Schwinger model, but has a richer structure. And another reason there is interest in this stuff is that the lattice Hamiltonian approach is somehow of interest to people doing tensor network methods and DM density matrix renormalization group. And it can actually lead very precise results. Much more precise, I think, than lattice Monte Carlo for these models. So it poses a challenge of extending this to 2+1 dimensions, for example. So let me conclude and thank you for your attention.
Thank you very much for a great lecture. So please ask questions. Let me ask one first question. I have several questions, but maybe there is a question from the chat. Give me a second.
Right.
Yeah, maybe I will read for everyone.
Yeah, this model was just a 1+1 dimensional model, like this, what we call a joint QCD2. It's a very, the model that I wrote down on the slide, just a single multiplet of Majorana, a joint multiplet of Majoranas coupled to a SUN gauge field. And then you add the mass for the fermions. It's very minimal looking model. When the mass is non-zero, it certainly is a confining model. The mass gap can be approximately computed for sure. Yeah, we computed this mass gap using light cone quantization already more than 30 years ago. But this exact derivation of supersymmetry, I think, is a new result that we were missing all these years.
So, any other question?
Can I?
Yes,
Can you hear
please.
me? Hi, Igor.
Hi.
Whenever I think about this mass gap problem, I am a little bit confused. While creation of a mass gap in the scale invariant theory is a formidable problem, but why is this problem in a lattice theory, which does have the definite scale?
Oh, you're asking why is it a problem in 1+1 dimensions?
No. In just 3+1 dimension. Once we have the scale of a lattice, then by the dimensional transmutation, in every other scale, we can express some mass scale in terms of that, the lattice scale. So the theory is provided with a definite scale, and why presence of the mass gap, which is a scale, is a problem at all.
Well, I mean, there is initially there is only dimensionless coupling in the theory, right? In the lattice
but the theory has the scale by given by the lattice, right?
Yeah, but that's this whole you don't want in the strong coupling limit you see confinement with extremely heavy bound states, right? Whose mass is of order 1 over lattice spacing. That's a kind of trivial confinement. It's definitely there in this. It's a very lattice-dominated model with extremely rigid strings, right? What you want to see is that as you adjust your bare coupling from large to small, these strings become dynamical, right? And string tension goes from 1 over A to lambda QCD. That's basically what you can only show numerically, and
but what I mean is that the argument of the dimensional transmutation is not enough to generate the scale if we are given some definite scale A0.
Well, I think
on the other hand, if we don't have any a priori any scale like an A0, then it's of course impossible to write down any QCD scale at all. But once we have A0, then I don't see what
the question is the continuum limit, right? You start with this lattice spacing, but then you have to send lattice spacing to 0, right? And anyways, I'm just repeating what everyone says. I think what people see on the continuum argument is just that you estimate the scale of baryons by where the running formally blows up, and it doesn't prove anything. On the lattice, you do see like that the scale you estimated does give you the masses, but you have to do a lot more to solve the theory, right? Yeah, I mean, this is where I think actually this, for example, so one toy model for this is the O3 sigma model, right? That has asymptotic freedom and has sort of IR scale generation. That's a much simpler model, but it's not a gauge theory. And what I'm saying is that if you start with this 2-flavor Schwinger model, that's maybe an even better model of QCD-like behavior, where you start with a completely UV finite theory. There is no, but then within when you go to the parameter region where M is much smaller than gauge coupling, then you start seeing this log running in the effective BKT series or Sine-Gordon theory. So. And I think we do see evidence of dimensional transmutation. We see this, the mass gap is exponentially small compared to G, which is like inverse lattice spacing in the lattice theory.
Okay, can I ask you one other question about the string theory example?
Mm-hmm.
So is there any examples where the boundary theories doesn't have any scale, but they still, we can generate a model where it produces
Well, in the model that I showed, this deformed conifold model, the boundary theory does have a logarithmic running. And basically, because of this log in the boundary theory, we have generate the confinement scale. I think the goal in these gauge gravity duality is to find something where you can see logarithmic running in the regime of weak curvature, and there are very, very few models like this. I think this duality cascade that I found with Zeitlin and Strassler is one such model, but there are very few models where you can see.
In that model, how RS was introduced?
Excuse me?
The RS, which is generated by some bulk scale.
Yeah. The RS is it's just a parameter which you can relate to the original. But RS is just the position of naked singularity in that solution. But there is something that replaces it. I mean, in this full metric, which is non-singular, you see the analog of RS, and it's related to this epsilon parameter, the deformation parameter of the conifold.
So RS cannot be related to any, the boundary scale?
No, RS is, RS really appears through dimensional transmutation, if you will. Yeah, it's an infrared effect, like there is a complicated RG flow and then it terminates in the infrared. I can suggest some reviews that, for example, I have a review from 2001, like remarks on warp deformed conifold, where this is reviewed.
Yeah, because almost all of the models I know in string theory is the bulk scale is generated by hand.
No. Here it's really dynamical. Yeah.
So,
I mean, there are lots of models where people just put like an infrared wall.
Yes.
No, here we want to see the dynamical dimensional transmutation, and it really happens through this like the undeformed conifold becomes deformed, and this epsilon dictates the scale of the string tension and of the bound states.
Yeah, I appreciate the logarithmic running, but I was interested in actually how the scale is set was generated in the bulk.
Well, if you don't put this epsilon, the solution is singular. Once you put this epsilon in
singularity,
then it's like the QCD scale is the sort of one scale that this theory has.
Thank you very much.
So, are there other questions from the audience? Let me ask several questions. So you said you talk about this numerical simulation of the Schwinger model, maybe 1+1, and then also generalized to this non-abelian case. Maybe when you say quantum simulation, it's a Monte Carlo simulation. or you are also talking about both Monte Carlo and the quantum computer?
Well, one possibility is just to build a cold atom chain, right, and conduct experiments on it. I mean, that's
I
sort of
see.
one way to. Yeah, like I know for example, Peter Zoller and the Innsbruck group, they built this 51 atom chain for trying to simulate Schwinger model.
Oh, I see. Non-abelian or abelian? I mean, Schwinger model is abelian when you say.
Yeah, abelian. Just the
Yeah.
one flavor abelian model.
Yeah. What about the QCD2? Two-dimensional QCD case.
Like a Toft model, say SU2, that is not done yet. No.
I see.
No. Yeah, I mean the next goal could be like indeed. Well, Toft model is large N, but just take SU2 gauge theory or something
I see.
with fermions.
Uh,
Yeah, I mean, I think, and another, I hope I convinced you that the one with these Majoranas is very interesting.
mhm.
I mean, that's probably harder to build.
Yeah, that's right.
But when we write down this Hamiltonian, we sort of have like a mechanistic model, right? States on a site and they're coupled together. One has to do a lot of group theory to solve for the spectrum. Yeah, if you look at these lattice Hamiltonian for a joint UCD, yeah, in these papers we looked explicitly at SU2 and SU3 models. The complexity here grows up a lot with N. Like so, SU3 is already very complicated.
So is there any sign problem there? The model case.
Time?
The sign problem because
no,
of the.
no. That's why the Hamiltonian is so good.
Oh, I see.
No, yeah, you solve the doubling problem. There is no sign problem.
Oh.
Yeah, I think there is some way maybe I've seen recently papers trying to do these Majorana joints with the Euclidean like overlap fermions, and that's very tricky. But here it's just like it's like coupled Kitaev chains with some coupling between them, and
I see.
yeah, that certainly avoids doubling and avoids the sign problem. The results actually show impressive agreement with light cone quantization, for example. There are many cross checks.
Okay.
Yeah.
And I have one more question about the your Simon collaboration. What's the current goal in the collaboration?
Well, I mean, the most ambitious goal is to understand the mechanism for confinement in some specific 4D and 3D models.
Oh.
And also understand like the dynamics of confining flux tubes more precisely.
I see.
Yeah, and people are doing some lattice calculations. There are definitely progress on like the structure of the confining flux tube. And now people are studying actually the so-called baryonic junction of flux tubes, which is an important parameter in models, like where 3 flux tubes meet in SU3 gauge theory to make a baryon.
So both the analytic and the numerical.
Yeah, definitely there is a lot of numerical work. Yeah, that's sort of the difference now compared to even 20 years ago. I think the numerical work has progressed. And for 1+1, this Hamiltonian method actually works very well. It's much harder in 2+1 already, but we're hoping to, because ultimately Hamiltonian method is more physical. And you can study time-dependent processes.
Okay, so is there any other question from the audience? If not, let's thank Igor, again for the very nice talk.
Yeah,
Thank you
thanks
very
for
much.
having me. Yeah, thank you.
Yeah.
Mhm.
It is a night, right? In the New York.
Yeah, it's getting, it's 10:34 p.m. So
Oh, wow. I see.
Mhm.
Thank you very much. Yeah.
yeah, thanks for having me. Yeah,
Yeah.
yeah,
Okay.
hope
Thank
to
you very
see
So
much.
you.
hopefully you can visit Korea maybe next year or
Yeah. I'll definitely try. Yeah,
sure.
yeah.
Okay,
Thanks.
see you.
Mhm.
Bye.
Yeah, be well. Bye.
Bye. Thank you.